got to finish up chapter 3. The handout, I think the handouts are valuable, beneficial. So this one, we'll close down chapter 3. So I've talked to some of the other Math 2 instructors, we're just a little bit ahead of where they are. We're almost the same place some of them are. Here's where we're going to close down. We're going to leave polynomial functions that you love, which will be quizzed on tomorrow, into chapter 3, ends with rational functions. A headache. I'll just warn you ahead of time. Can be a headache. So after I start rational functions and show you something about a rational function, and then you reflect back to polynomial that we were doing before the break, you'll wish you were back on polynomial. Because these can get crazy on you. And you'll see why here shortly. Bella, what was that question?
I was going to ask, how many chapters do we have to get through?
All that's on that syllabus. But all the chapters, some of the chapters not covered in the Math 2, in the textbook. But those that are to be covered was listed in the syllabus. Okay? Guys, some of my students, by the way, Bella, I'm glad you asked. I asked some of my students, and some of my students are working ahead, which I want that the way I had the syllabus written. I want you to work ahead. And I think one of my students is in chapter 4 already doing logarithms, and I haven't mentioned the word logarithm. But that's in chapter 4 coming up. So he's already worked into chapter 4 and getting ready for me by the time I get there. Okay? I'm closing down chapter 3 today. You, Susan, are you extremely busy? Try this, and I think I've brought enough copies here. That's one out. Mr. Park, help me out. Guys, keep in mind, you look at this. This is the conclusion. Chapter 3. Thank you, thank you, thank you. Thank you, guys. Everyone has a copy of this? Now, before I get started, I sent out, check your mail, this is midterm, after class. Check your mail, because I did send out the, what they call a survey, where I gave you statements as you're doing a good job, keep it up. If you're not doing great, check in the math lab, this is going on with you, that's going on with you, just to keep you up to date so you'll know the way the instructor feels. Just in case you're not up to where you should be, it's time to get up there. In fact, if you're not up to where you should be, you still have time. That's why I sent those out to get up there. I don't want to wait till late to send those out. So I sent those out today by mail, just sort of giving you a complimentary message if you were doing well. Maybe something to suggest you do if you're not doing that well. So guys, check your mail there for that. I want all my students to get through. I've never had a class yet, as long as I've taught, where every student passed. Never. Never. I wish I did. I don't think any professor in this world, I don't know, maybe, has had a class where every of the 45 or 30 students passed. I just never have had it to happen. I have not heard of any professors here where that's happened. If I get most to do it, I'm happy. Very happy. So a certain percent I'm looking for, the percent of students I want to pass, I get that, I'm happy. Very happy to get that many students through a course like this. That means if you do not step up, guys, you may have to repeat. I hate to say that, but you may have to repeat somewhere, maybe summer or fall, repeat the course, or take it online somewhere else, or whatever. I hope that does not happen. And right now, it's looking pretty good. Those quiz scores, I think, are helping. And my guess, I had, what, 15, was it 15 A's on the last quiz? I mentioned the number. Quite a few A's on that last quiz number 4, I think it was. So we're going in the right direction. Absolutely. Who knows, it may be possible that I will have a class where every student has a C or better at the end. I'm hoping. Now, let's get back to this. I will be very, very careful on this. It's going to take a little time. And let's start out with part 1. Yes, they call these, to conclude chapter 3, they call these rational functions. And before I jump into it, give you a description, take a look at some of the work on the handout. Oh my goodness, and here comes that word function again. Quickly. We started out with quadratic functions. We've done polynomial functions. We had absolute value functions. They attach the word functions to these. Here's another type of function. Should pass the vertical line test, the graph. They're called rational functions. Now, your textbook gives for a description, they look like this. R for rational, and it's written like this. P of x over Q of x. In other words, it looks like a fraction, a ratio. Now I see the word ratio in the word rational. So these are in the form of a ratio, a numerator over a denominator. Now, guess what the P of x and Q of x are representing? Give me an idea of what you think P of x and Q of x are representing in this fraction or ratio. Give me an idea. Remember why your textbook used, for example, P of x? Polynomial. This is supposed to be a polynomial function on top, another polynomial function in my denominator. So it's a polynomial over a polynomial with an exception. The bottom part, denominator, we know this, cannot be 0. We began to find. So it's a fraction, ratio, and we're supposed to graph them. Now, I will start out with the most simple rational function I can think of, is this one. 1 over x. That's a fraction. The numerator is 1. I can consider that to be a monomial from middle school. And the x, of course, is a one-term polynomial, x. So it is a rational function. I like to sketch it. Now, our students in class, I guarantee you, will say, Professor, I think I know what this one looks like right now. I think I know what 1 over x, your first rational function example, looks like if I should sketch it. Does anyone think they know what it looks like? Yes. A V-shaped graph. Now, if it's a V-shaped graph, it's an absolute value graph. Alex.
It's like 2 graphs that go like that, but never touch the x-axis.
Okay, I see the way you described it. You're saying, Hannah, I heard what you said also. But, look at this. And we're going to see why. That's the most simple rational function, 1 over x. Alex is telling me, Professor, I may have seen this on the handout I gave you weeks ago on the parent functions. I think it was on that sheet of parent functions. I think it was. But Alex is saying, Professor, it looks like this. One branch is there, and the other branch is down here in quadrant 3. There's a graph of 1 over x. Now suppose you go to UCLA, USC, and they ask you to graph 1 over x, and in your mind you've forgotten. What could you do as a clever student to quickly get the graph that you may have forgotten its shape? What is one method you could use to quickly get the sketch? And let's say you've forgotten the shape. And you want the graph. What would you do? Do it again.
Plug in X value.
Plot points. I know every student in this classroom has done this somewhere. Is that true? And form the table. Put in numbers and form a table, then plot the points from the table, connect them, you'll get this for 1 over x. Now guys, here's the issue. These are discontinuous functions. We'll use that word. A discontinuous function. In other words, not like my polynomial functions before the break. Those polynomial function sketches were all connected. Weren't they? Nice and smooth graph. These are not connected. So if I ask you to graph a rational function, don't expect it to look like one of those polynomial functions. These are disconnected. They're called discontinuous functions. Guys, the most basic one looks like that. Now here, let me point out a few things about this basic graph. On the side, can someone please answer this question for me? What's the limit as x gets large for this function? Let's do some calculus. You have the graph in front of you. The red graph is the graph. This says, now, can you give me an answer for what happens as x gets large? And I could use large numbers in this table and play with it. Or since I have the graph that says, here's the x-axis, they're saying, please, without the table, here's x, make it go forever. You're traveling along the x-axis forever, and you're dragging that graph along with you. What's my red graph doing as you walk to the right forever, and you drag that red graph along with you? What's the red graph doing? As I hold it right here and I walk this way forever.
Approaches 0.
It's approaching 0. Is it approaching the x-axis? Which is 0. It's getting awfully close to 0. Will it ever get there? No. I don't care how far you walk, and that's what this means, go forever on the x-axis, and you grab hold of the red graph and you walk this way and out through that wall and out through the next room, whatever, you'll never get to 0. It'll never touch the x-axis. Will it get close? Yes. Now your calc instructor is going to give you a particular number they want it to get close to. Maybe they want it to go all the way out to, and start this way, and you may say, Professor, I got it out to 0.000001. Not quite 0, right? And you may want to take it out a little bit further and get a little closer. It'll never get to 0 though. So the calc instructor will let you know how close they want it to get. Here, we're going to just describe it like this. And guys, in this case, it is. Look at this. The answer is, as I heard, 0. Now, would it happen on the other end if I wrote my limit like this? Let me describe for you what's happening here. This time you're going in this direction, to the left, negative infinity. You're dragging that graph along with you forever as you walk this way on the x-axis. What's my red graph doing? As you grab it and you walk this way forever and out the wall there forever. Where's it going?
Also to 0.
Is it also approaching the x-axis, which is 0? But it's underneath there. It's okay. But is it getting close to 0 again? Now, what did I just describe for this 1 over x graph? Tell me the words I need that would be appropriate based on what we did before the break. What did I just describe here? This is the end behavior. My 1 over x graph. Now we'll get you ready. Soon, in a few minutes, I'm going to start graphing the more complicated rational function. This is the most basic one. Also, you'll have to know before I get to the more complicated ones how to answer this. Now look at this, it's going to look crazy. I like to find the limit as x is approaching, not infinity, not negative infinity. I'm going to approach 0. Whoa, you guys guys are so accustomed to the end behavior, which I love, you're going in this direction for the end behavior. Now I'm saying, no, now think for calculus, you're coming in this direction. You're approaching 0. Now, can someone tell me, could I approach 0 from the other side?
Yes.
That would be coming in like this, and you're approaching 0. Therefore, since I can approach 0 from both sides, I'm going to tell you which side I want you to approach from. So if I want you to stay on the right of 0, they will put a superscript of a positive sign. So let you know which side to approach from. I'm going to get ready for the next one. We're going to answer this here shortly. The next one might be written as, find the limit as x is approaching 0 from the left, over here, left of 0, and they will place here a superscript, not exponent, of a negative sign, and they're going to ask you to get the answer. So I've got to put those little superscripts on there to let you know which side to approach from. Okay, let's try the first one. It says to approach 0, right here, from the right. Well, this is on the right-hand side of 0, isn't it? So you're coming in this direction. Can anyone tell me the closer you get to 0, as you come in this direction, and you get close to 0, you're not going to touch the 0, you're getting close to it. What's my red graph doing? Is my red graph rising forever? The closer I get to 0, is my red graph rising? Therefore, an appropriate answer would be infinity. If I approach from the other end, in other words, on the left now, the left of 0, you're coming in this direction, towards 0. As I come into 0, I'm not going to get to 0. As you get close to 0, what's my red graph doing over here? It's dropping down through negative infinity. They give a name for a line that does that on one of these rational functions. I have a line that does that. I have the y-axis, which is x is equal to 0. Some of my students may know what vocabulary I'm looking for right now before I jump into a more complicated problem. Does anyone think they know what this line is known as? Where you approach from one side, approach from the other side, you get infinity on one, negative infinity on the other, or infinity, infinity, it could be both infinities. Does anyone recall what that might be? And then we'll look at it. It's an asymptote. And in fact, is mine a vertical asymptote? Okay, so it's a vertical asymptote described here. Now, I thought about this. I always do my planning. You got the handout again. We can't get through all this today. No way am I going to get through all this. Alexander, since you're close by, would you jump down to the 4 examples I have down there and tell me what is the first rational function down there we are to graph?
R of x equals x minus 1 over x squared minus 4.
Hang on. She said, Professor, it says the sketch is. Can anyone tell me anything at all that you could do with this algebraically before I jump in and start reading what those steps are on the handout? Is there something algebraically I could do at this moment? I could factor. A difference of squares. That looks better. Now, before I jump in and have a student start reading for me, please tell me, class, not just one student, class, can you identify what the domain on this function will be? Just domain. We talk about domain in here. What's the domain on this first rational function? X cannot be? Yeah, makes a 0 denominator. So x cannot be, I'll just write like this, plus or minus 2. Now, can anyone give me a guess as to what you think when I finally sketch? I haven't sketched yet. When I finally start sketching to get the sketch of this thing, does anyone think they know what's happening at plus and minus 2? Because they can't use them. They're undefined. How's that undefined going to look, do you think, on the sketch? That's going to be an asymptote. Just like this thing had an asymptote here, and I could not touch it. It was undefined. By the way, guys, if I should replace x by 0 here, would that make this undefined? In other words, my domain was x cannot be what, 0 here? And that's exactly what happened. So when I get to 2 and negative 2, I'm going to have 2 vertical asymptotes to worry about. Now I need some help. Who would like to read? Because there are certain steps we've got to follow, and we can't do all these today. I need a volunteer just to read up to a certain point, and I'll stop you there. Billy, go for it.
So step 1, find the domain of R of x. Do not cancel factors in step 1.
Thank you. We got the domain done. Step 1 is finished. She's got to be set up there. Okay, step 2.
Simplify. Write R of x in the lowest terms.
Okay, let's do that right now, which we've already done, but they want that. So R of x is equal to this. Guys, watch carefully.
Really quickly, so the vertical asymptotes are what x cannot be.
Exactly.
Okay.
Now, tell me more. Billy, what's step 3?
Name the intercepts x and y of the graph.
Whoa, whoa. Now they want this. And we know how to find the x-intercept for any function. You set what? Set it equal to 0. Guys, if I go back and set my function equal to 0, and we use the original function they gave me, it looks like this. That's the way you find the x-intercept. We've done that in class here. Solve this, you can do a cross multiplication, or multiply both sides by x squared minus 4. Please tell me, when you simplify this, will you end up with it looking like this? Which says x is equal to what? 1. And we'll write this as an ordered pair, it looks better. There's your x-intercept. I'm gaining some information about what this graph may look like. Y-intercept, we know how to find it, we got it in here. You find R of 0. And we'll just go back and replace all those x's by 0, and guys, in the original, it would look like this, with the x being replaced by 0, which I think comes out to be a positive what? 1/4. Did I do that correctly? Better yet? Yeah. So far, so good. Yes, no? Okay. Billy? Okay, for today, let's see if I can answer number 4. What's number 4 asking?
Determine the vertical asymptotes, if any, of the graph.
Hang on just 1 second. Now they want to know, where are those vertical asymptotes located? Strange word, asymptote, the way it's spelled there. Asymptote. Where is the vertical asymptote? Could be more than one. And I think we decided, where are they located? 2 and negative 2, we think. So let's write this as, that's one at 2, and the other one's at negative 2. Alexander, what you said earlier to me, I think it's good. Just look back here. Now, Billy, I think there's one more step for today. I'll do the other steps Wednesday. That might help me to get this graph started. What's step number 5?
Determine the horizontal asymptote, if any, of the graph.
Hang on just 1 second. Horizontal asymptote. Guys, let me just abbreviate that strange word. Oh my goodness. Go back to my basic graph. Did my basic graph have not a vertical, it had vertical, yes. Would you say the basic graph over here also has a horizontal?
Yes.
Was it the x-axis here? Was my graph getting close to the x-axis? The further I went out this way.
I
And the further I went out this way forever, I'm gonna get close to the x-axis, which I think we described here. Is that true? So if I knew what the end behavior of this that she asked me to find, if I knew what the end behavior of this graph was, that's what they want. Whatever the end behavior is, that's where my horizontal asymptote's located. Does anyone have an idea? How on earth would you attempt to find the end behavior of a graph that looks like this, which is not polynomial, does not depend upon the first term, like you're accustomed to for a polynomial? This is a rational. Does anyone have an idea? Let me do this right here. Billy, I'm gonna do it like this from what you're asking. I'm gonna write this as limit as x is approaching infinity of my, here we go, function. If I know what that is, we're good. And of course, on the other side, x is approaching negative infinity. Same function. If I can get the answer for that, we now know where the horizontal asymptote is located. And that'll be my last thing I need for today, then we'll put all this together and graph it. Does anyone have an idea? As you make x get large, what on earth, as you start replacing x by large numbers, and you calculate this entire mess here, what do you think it's getting close to? The larger the number is that you put in there. It's difficult to see right now. Okay, I hear Ignacio. Let me take that function and put it in factored form. Better like this. Guys, these two are equivalent. He says, Professor, I think if you start replacing x by a large number, and you do a calculation, let's just visualize a large number. Let's put 1,000 in there. That's a large number for x. Put 1,000 in there, guys. If I put 1,000, you got this. Thousand is fairly large. Let's see what happens here. On top there, what is that? 999, I guess? Is it?
Yeah.
Down here, what? 998 times 1,002. Can anyone tell me what might this be close to? Or what it is? That's going to be my end behavior. I know I've got some big numbers. I could go larger. I thought 1,000. I could go up to 10,000. What do you think it is? What do you think this is? I got 999 up here. Mr. Park, do me a favor. Don't make a mistake. Divide this out for me.
Okay.
Take 999 and divide it by this product. I just want to see what's close to. Then we'll see if we can sort of see without a calculator. I want to see what it is.
That's like 0.0009999.
Oh my goodness, so it's close to what? 0. Mr. Park, you okay there? This guy made the highest score on his Math 11 test the other day. Was it Math 11 or Math 13?
That was 13.
13, right?
Yeah.
13. That's the highest score in the class. And here we are privileged to have him as a tutor. Okay, he says it's close to 0. Avery, suppose I went a little higher, because this says x gets large down here. Suppose you say, Professor, you tried 1,000, suppose I put 10,000 in there. 10,000 minus 1, get that number. 10,000 minus 2, 10,000 plus 2. Do you think maybe if I should ask him to do it for that, it might be close to 0 again?
Yes.
I think with those large numbers, it looks like it's approaching 0. I'm trying to think. Yes, okay. We're going to say this is equal to 0. What do you think might happen if I say now replace x by some negative attached to it, some large number? maybe a negative 1,000. I tried positive 1,000. I tried on the positive side. Now suppose it says x is approaching negative infinity. You say, wait, Professor, what does that mean? That means now we'll put a negative 10,000. And make that what? Negative 10,000 or negative 1,000? Let's stick with that. Subtract 1 over negative 1,000. Subtract 2. Negative 1,000 plus 2. Can anyone tell me what on earth do you think that might be close to? You think it'll be 0 again? I tried another number there. So I think down here, might I get 0 again? Really? We need some help. So I think a good way to do this. Billy, on that horizontal asymptotal handout, did I have underneath there to close this thing down for today? Did I have something else written with it?
With the horizontal? It says important.
Okay, what to say?
Or, actually, there's a note here. I'll read the note.
I could read the note.
The horizontal asymptote will describe in behavior of the function.
Oh, that's what we did in behavior. Tell me more.
To find the horizontal asymptote, we will use the end behavior of r of x equals 1 divided by x.
Okay, now I've already done that. So 1 over x, guys, the most basic rational function. What was it doing out on the ends? This. So if I can use that fact on this problem, I'll have it, for sure. Now what can I do? Billy, thank you so much. I'm going to take my function, oh, right here it is. Guys, I'm going to do a little calculus, but just a little bit here. What's the highest exponent you see on the original function? When you scan the numerator, you scan the denominator, what's the highest exponent you see? Square, 2, x squared. Now divide, this is a little technique in calc. Divide everything by x squared. The numerator, denominator would look like this. Everything, every term, by the highest. Little technique, I'm going to show you. So first find the highest, then divide everything by it. Now clean that up. Guys, if I clean this up, this is 1 over x from algebra. On the end, I could write it for a reason as 1 over x times 1 over x. That's 1 over x squared. Down here, I get a 1. And to write or rewrite 4 over x squared for a reason, I can write like this. Is that true? Guess what I get to do for everywhere I see a 1 over x? It takes me back here. What was the end behavior on 1 over x? 0. So every 1 over x I see, I get to put a 0. Based on that over there. 0. 0. 0. Now we're not talking about quiz scores. 0. So what is that? Looks like there's a 0 on top. Over what is left in my denominator? 1. Is that true? Oh, I see. It looks like, whoa, we are going somewhere else. By the way, is it 0, guys? Am I left with 0 over 1? Which tells me after all that effort on this first example, Billy, my horizontal asymptote is located at 0 as it was over here on this basic graph. In other words, I'm going to let this like this. It's the x-axis. Billy, please tell me, was there anything else there besides a note?
It says important.
Okay, what's it say about important?
It is possible for the graph to intersect its horizontal asymptote.
Are you kidding? Now don't do this, don't mess your notes up. She's saying, is it possible? I don't think I'm gonna give you an example today on this, But she says, it's possible, Professor, this graph is good, guys, don't miss this graph. It's possible, and mathematics, anything is possible. It's possible that if you stretch this red graph out, that's not what really happened on this one, that out here somewhere, you know how math is, it might cross over. Out there somewhere. Please tell me, is it still following the x-axis? Is it still getting close to the x-axis but it fell underneath it? I don't mean this. I mean it stays close to it, hovers around the x-axis. And that may be possible. We're not going to do one like that today. We're not going to do one like that today. But she's already told me it's possible. It may happen. Billy, was there anything else there before I draw the grid here and try to graph this?
In step 5?
Oh, what's number 5 saying?
Oh, that, the important was the end of step 5, there's step 6. You'll
Now what's step 6?
Determine the oblique.
Oh, whoa, we're not going there. Not today. And when I finally get it tomorrow, show you an oblique, you'll wish we would not go to a period. Because the oblique is something else, another type of asymptote. Guys, with all this information, Billy, you're telling me this is number 1 at the bottom of the page. Here we go. Then I'm going to give you guys a little practice problem here shortly. I gotta watch the time. Let's put all this together and see what this graph may look like. For your first example. Okay guys, it's up to us to put things together. I always like to put the x and y intercepts. By the way, did I find the x and y intercepts? I did. That was the x-intercept. That was the y-intercept. We'll place those first. Let's go to some partial credit here. I've got a 1. And also we have a 1/4. Put a 1 here for a reference. 1/4. Got those out of the way. What else do we have here? We have vertical asymptotes. We've got 2 of those. One's out at 2, and the other one's -2. We said it's going to look like this. That's going to be a vertical line here, and a vertical line here. Done. True? Just put everything on the grid. Horizontal, after a really lengthy discussion about how to find the horizontal, the end behavior, we said, Professor, it's this. It's the x-axis. Put that in a different color so we're not confuse it. It's this. Extend this just a little here. Let me step out of the way here. The x-axis is the horizontal asymptote. I think, is that all we have to work with? Now I'd like to see where the graph is. Otherwise, this is not a continuous function. It's disconnected. And I said, Professor, what's going on? It's so disconnected. A part of the graph is over here to the left of this vertical asymptote. There's something happening in between here, and something happening to the right here. You guys focused? Right there? Okay, so there's 3 pieces to this graph. They're not connected. Now, you say, Professor, what's it going to look like? I'll give you a possibility and you guys try to decide which one it is. On the left, to follow those asymptotes. A student may say, Professor, it might look like this. That follows the black vertical asymptote at -2. It follows the red, does not touch it. Might it look like that? The vertical gets close to the vertical, it gets close to the horizontal. Is that a possibility? Another student may say, well, Professor, could it be like this? We've got to decide which one. might look something like that. Is that also following the red and following the black?
Are they always like, is one always up top and the other always going down?
Well, not necessarily, not necessarily. All depends on the function. All depends on what function they give you. Guys, it can't be both. Wouldn't pass the vertical line test. Wouldn't be a function. Anyone tell me how would you distinguish? Is it the one on top for this one, or is it the one on the bottom? Okay, now, tell me why. He's telling me, Professor, I think it's down here doing this, not up here. Tell me why? Well, the parent graph, something else that I think I would be cautious about, besides maybe looking at a parent graph. There you go. I think I heard someone say something.
Oh, is it?
Okay, what you're looking for is it negative? That means it's down here. Is my function negative? Or is it positive? What could you do easily as a student to see? Is it going to be above or below for that branch? I was just plugging a number real quickly. In other words, there's lots of numbers out here to the left of -2. Let's try -3. And you don't have to really do a quick or an exact calculation. Let's plug in -3. Where's my function? I guess way back here. I'm going to replace or find r at -3. Guys, this is -4, -5, -1. I placed that -3 in there correctly. Yes or no?
Can we go back to our horizontal asymptotes and notice that on number 2 there, it approaches -0?
You could, hang on, I just want to point that out. So this is -4 over a +5. Is that true?
Yes.
What does that tell me? Is it going to be above or below?
Below.
Is it going to be below? I was talking about negative. Is it negative below? So is that graph short enough, as I heard a student, I think, tell me earlier, is the graph I'm seeking, based on that check, is it below? I just placed a number. I placed -3. You could test -4, -5, something to the left of -2 to see where it is. In between, well, you got to pick up these two. So there's also a piece called the in between. So this graph is all disconnected. You may have an idea what it looks like there without plotting points. Does anyone have an idea of what that shape looks like? And you got to pick up this, you got to pick up this, and you got to follow those asymptotes. Give me an idea. Now we'll use a different color for the next piece. Anyone have an idea what that shape may look like caught between? We got to pick up the x and y intercepts. Go for it.
Like this?
No.
It goes down and,
Okay, got you. Are you saying like this? It's a possibility.
yeah, and then it crosses,
Like this?
and then it goes down.
You saying, Professor, to pick up the x-intercept, y-intercept, and get close to those asymptotes but do not touch them? Might it look like that? Is that true? And you can plot points to make sure. Now we got one more piece of this discontinuous function. It's out here. So we'll use a different color. Is it up here or is it down here as I had to worry here? Is it up here or is it down here? What would you do to see what the graph looks like on the end? I would try 3. You can just plot a point. Could I try 3? Something out to the right of 2. And on the side here, find r at 3. Now think r at 3, guys, is 3 subtract 1, that's a 2. 3 subtract 2 is 1. 3 plus 2 is a 5. What do I end up with? Positive 2/5, that means I'm above. So my last piece is above, positive. It's got to follow those asymptotes and do not touch those asymptotes, and it looks something like that. There's your graph. Now, if I had met you at the door the first day, and I remember back in the day, some instructors would do this, they met their students at the door and asked them to answer a question. If they didn't answer it, no, you can't add the class. Can't do it. Can you imagine if I had met you at the door and asked you to graph this? I would have no students. SMC would quickly send me an email. Randy, you have 0 students. Well, I asked them a question at the end. At the beginning, I thought they would know how to do it, and nobody got it. My enrollment's dropped to 0. Now, that would just be crazy if somebody did that, wouldn't they? Okay, I would never do that. Guys, by the way, does this make sense? The way we approached it? Now, I'm looking at my time here because you guys are going to practice something here shortly. That's just the first example of what they call a rational function. Look how disconnected this thing is. Okay? Look how disconnected. Now, I'll see before I answer questions here. Can you look at this graph and tell the class, we have a domain. Can you tell the class based on the graph, what's my range?
It's negative infinity to positive.
It is. This piece right here saves me. Negative infinity drops down forever, rises forever, so negative infinity through positive infinity for the up and down of the range. Is that true? Alexandra, what was that question?
So Avery knew that it was that graph, but if we could get a little more explanation as to how.
Avery, what do you have in mind?
With regards to the horizontal.
See, your students are listening to you. Oh,
Yeah, so if you look at the number 1 there, the first horizontal
Right here?
asymptote, you'll notice that it approaches positive 0 because it's never negative.
well, 0 has no sign, no call it positive. You're approaching from the infinity, positive
Yeah, well,
infinity.
0 subscript plus, right? And
Oh,
then the
now,
other
if you're
one-
approaching 0 from the right.
Yes,
Hang
and you'll
on,
notice this,
look at this, look at this.
and you'll notice it's the other,
Avery, hang on. That's what exactly beautiful.
that will never give you a negative.
Since I have the graph in front of me, let's approach 0 from the right. Guys, here's 0. And be careful. You're supposed to be approaching 0 from the right.
Is this where the X and Y intersect?
What's that?
Is this where the X and Y intersect?
No, he's got something else in mind here. Okay, now what do you think the answer would be as you approach 0 from the right? Now, I know where 0 is, right here. And be careful, you're approaching 0 from the right, and closer and closer and closer to 0. Where's my blue graph headed? Oh, this is interesting. You just did a calc problem, but you haven't given me the answer yet.
To infinity.
No,
1/4.
no. Oh, yeah, thank you. The closer you get to 0 in the green here,
Oh, well, it approaches 1.
what's my blue graph doing? Is it getting close to 1/4?
Or 1/4.
That y-intercept, right here. Is that true? Now try it on the other side. What's the limit? As x is approaching 0 from the left.
Also,
And that means you're approaching it from this direction this time. And you're awfully close to 0. What's my graph doing? Is my blue graph coming down, getting awfully close to that 1/4 again? Yes or no? Would you guys agree? Is it dropping down close to 1/4 again, the same point? Right here. I don't know whether you have something like that in mind, Alexandra. I think you asked me, rephrase that for me.
I wanted to know how, like, he connected the X and Y intercepts to have that graph, or like the line, I guess.
Oh.
Yeah.
well, if it were going up, then we know that it crosses, right? So if it were going up, then wouldn't you see another?
Oh, you mean right here, in here?
Yeah, because it crosses the way that it does.
Is that the part you're talking about, the blue part?
Yes.
Yeah. And I think what he's telling me is,
Because it crosses.
yeah, that's crossing, yeah, but it's got to stay close to what, this asymptote.
Yeah,
Comes down, picks up that y-intercept, picks up that x-intercept, and goes down forever.
yeah, because we would see an x-intercept on the other side if it came from.
Gotcha, I got you, that's what you're asking, thank you. Yeah, if I had tried, I think you're saying about this. You say, Professor, why didn't you do it this way? And up in here, so, if I do it this way, am I gonna cross the x-axis in here? And there is no x-intercept here. So I cannot have it come up like that.
But how do we know that the blue line is not like a parabola?
Oh, beautiful. You're saying maybe turn, listen to these questions, maybe turn this thing around and go up like this?
No, I mean, you
Well,
can still
it touches that,
touch the one.
that second
but
point.
go
Are you
back
not
up,
all the way down to one?
And then goes back up.
And then, whoa,
So it looks like this,
whoa.
and it just goes to that point, and then it goes back up.
Look at this.
So they
Nothing.
look like this, the asymptote looks like this.
What's it? He asked this. He said, Professor, could it do this? I think that's what you're saying.
Yeah.
Yeah.
And not this. I'm gonna erase this by doing this. I'm gonna erase it. I got some mathematicians in here. Okay, one tell me, you turn your quiz in when you finally have a quiz on this. And you turn your quiz in, how would you know, Professor, I think you had it correct the first time. And I love what Ignacio told me though. I think, Professor, you had better leave it in the blue. Now, how could I distinguish which is which? Is he right and go ahead and make it look more like a parabola? Or am I correct where it should go down like that? What could I easily do, just check to see? Agree? No, keep it the same. What could I do? I heard someone say, could I plot a point?
I can be over too.
Could I plot a point? Bella, was you gonna say plot a point maybe?
No.
Oh shit, well, let me plot a point first and see what you get. I have. If I plot a point, Ignacio, if I'm close to 2, like 1 and 1/2, I would go back to my function replaced by 1 and 1/2. Watch what happens here. I'm gonna put a 1 and 1/2 in there. 1 and 1/2, where am I? Oh, here it is. 1 and 1/2 subtract 1, guys, that's positive 1/2. 1 and 1/2 subtract 2, is that a negative? 1/2. I'll put the signs. 1 and 1/2 plus 2 is 3.5, positive. Is that altogether negative?
Oh, yeah.
Should my graph be below?
Also just plot 1 point before the asymptote.
That's all you need.
Gotcha. Okay.
That's all you need. Wow, I wish other professors could hear this conversation. Now, I heard Bella, what were you thinking?
I was gonna say it's not even, so it doesn't bounce.
Oh, hold on, she said, wait, she's even thinking about the even, odd, where the crosses or touches. And she says, Professor, I think these factors down here all have on the outside, do they? An odd exponent. She doesn't see anything even, so she thinks, no, it's not gonna touch, it's gonna cross, and it did cross, didn't it? Bella, you're right there. Guys, let me check it, see if I'm correct here. Is that graph finished? It is. Now look how much time it took me to do one. To do one. Vertical asymptote, horizontal asymptote, intercept, and this is the first time some of my students, I'm guarantee you in class, have ever seen something like this. Some students may have seen it somewhere else, and then all of a sudden reflect back to when you saw it and say, oh yeah, now I remember it coming back to me, I remember it. Some of my students have never seen it. That's why I very, very slow on this. Guys, this is just one to look at. Okay, here goes. I'm gonna finish it up. Then I'm gonna give you a practice problem. Would you like to see a practice problem maybe for the quiz? Maybe just take you a few minutes. Okay, on this one, let's try to find the limit as x is approaching infinity of that function over there. Make it look more like calculus. Now, a calc student would find that limit without looking at the graph. They have some calc techniques, right, Mr. Park?
Mm-hmm.
They don't have to graph it. Pre-calc, I don't have those calc techniques in here. We got graph it. Now it says limit as x is approaching infinity, that means you're walking out this way forever. What is my green graph over here doing as I drag it along with me as I walk forever to the right? Is it getting closer and closer to what?
0.
See, thank you. That's the answer. That's a calc problem. Now, is the same thing happening over on the other end? X is approaching negative infinity of this. Now you're taking the green graph, it's down here this time. It's going to drag it along with you forever like this. What is my green graph doing as you pull it along with you and you're going to the left forever? What's it doing? Is it also getting close to 0, the x-axis? You're doing calculus. Alrighty, next question, let's close this down. Find the limit as x is approaching, here goes guys, we'll close it down with this. Let's try 2 from the right of this function. I wish some of the calc professors could see what you guys are doing. They would be shocked. They would be shocked because your textbook does not even do this. Limit as x of this as I'm approaching 2 from the right. Guys, here's 2. So it says stay on the right-hand side of 2. You're approaching in this, like this, direction. You're approaching 2, but you're staying on the right. Can anyone tell me, as you approach 2 from the right, what's my green piece of the graph over here doing? Is it rising forever? Infinity. One more. The limit. As x is approaching -2 from the left of this function. Guys, you've done a beautiful job on this. Okay, -2, here's -2. And I said this time, what, stay on the left? And the left of -2, is that over here? So you're coming in this direction? Thank you. What's my green graph doing? Is it dropping down through negative infinity? All that if there's calculus. But we're doing it based on a graph. Jeez. Does that make sense? That's just the first, I think I have 4 of those examples, don't I, at the bottom of the page? Yeah. We've done 1, so we've got some more to do by Wednesday. Now, oh boy. Hang on, hang on. Here it is. Just one real quick before we close down. You guys are probably wiped out by now. Let me find it. Here it is. Oh my goodness. This is a practice problem for the quiz tomorrow. You ready? We may not have, you know what, I may have students go to the board. And as soon as I have a student who says, Professor, I found one of the zeros. Okay? I'll have that student come up and show us what that zero is, and we'll try to find the remaining ones. We've got to get this done. And the little shop, oh my goodness, no. We're not going to get done. This looks so nice, and we can't do it in class. Oh, guess where that might show up? It might be on the quiz. I was hoping to do more. Oh, it looks so cute. You guys can't do it most of the time. So I'll see you tomorrow. Now, if you did not pick your quiz, I have your quizzes. Okay, now we'll talk about that one game, like a 2 over 1.